All right, so all the previous cases were horizontal circles, okay? Different cases of horizontal circles. Now we have a vertical one. That means that the force due to gravity matters. Um, in this case, we will see, first of all, what happens when an object is on the inner side of a vertical circle. Let's say we have a car doing this motion, just like the toy cars. Um, I don't remember their name. So we will see the two cases, the lower position and the upper position. Let's call them A, position C, just like I had it in my notes. What is going on? Starting from case C, again, we need to identify the forces. We do have the force due to gravity. Here we do have the force due to gravity, and the force due to gravity is always down. Do we have any more forces? Yes, we have the normal force, which is down again, because the cart, the surface it's moving is above it, so the normal force should be perpendicular. The normal force should be heading downwards. Do we have any more? Well, we consider friction to be zero. There are no other forces. Friction will be zero. They will tell you so, just to make sure that they don't want anything else to affect the problem. So what is the radial axis now? The radial axis, the axis that connects the object with the center of the circle, is this. This is the radial axis. This is the opposite. Let's call it x. So we do have that the sum of forces on the x-axis is zero, while the sum of forces on the radial axis should create the radial acceleration. Meaning that in this case, normal force and the force due to gravity work together as the centripetal force. So the centripetal force should be the combination, the addition of these two. Now, in most of these cases, what they ask for the lowest speed we can have, so it does the turn safely. What does that mean? We can see that the bigger, well, the radius of the motion is the constant, doesn't change. What can change is the speed. And the faster this cart goes, the bigger the speed, the bigger the centripetal acceleration we need and the centripetal force we need to have. The force due to gravity is the same, doesn't change. That means that the normal force is the balancing term, is the term that increases as much as needed for the object to do the circle, to do the motion. So we see that the normal force can change. In this case, the normal force changes because of the speed. Everything else stays the same. Now, we can say exactly the opposite, that as the speed decreases, the normal force needed becomes smaller and smaller, because the centripetal acceleration we need is not that strong, right? So we can find a certain speed where we will not need any normal force. The force due to gravity will be enough for the car to do the circular motion on the top, okay? That's the lowest speed we can have, and the object will still perform the circular motion. What will happen is that for an even smaller speed, the centripetal force needed is even smaller, meaning that the force due to gravity is not needed, like it's not fully needed for the centripetal force. A part of gravity will not be needed to be used as centripetal force. In that case, the force due to gravity will work as it knows. It will make the object fall. So we see that there's a speed limit, a lower speed limit that a cart has to have in order to do the circular motion safely. Okay, there's a low, like a minimum value the speed can have. For a lower value, the object falls because the force due to gravity is not fully used as centripetal force. All right, so the lowest speed is the speed for which normal force will not be needed. It will be zero, and only the force due to gravity will be used, fully used, as centripetal force. So that means that force due to gravity equals mv squared over r. Mass does not matter again. So we see that gr equals v squared, or v will be the square root of gr. So this is the lowest speed a cart can have here without falling. For an even lower, it will stop performing the circular motion. Now, when we do energies, we will see another perspective of this formula. Well, many perspectives of this formula. We're going to find it again.